Okay, today's lecture we will start the Laplace transform properties, or we will continue with the transform properties. So today's date is the 21st, which is Wednesday. The expected reading will case 95 to 98. Then in Friday, the 23rd, the reading between 98 to 99. And on Friday, the due date for homework number 6. And you can go to Canvas, see what are the details on homework 6, see what you need to do. Then next week, the 26th, will be Monday, so the reading will be page 99 to 104. And Wednesday, 28th, the readings between page 104 to 106, and it's also the due date for homework number 7, which will be in next Wednesday as well. Then in Friday, which is before the spring break, there will be no class. Okay? So we will have a spring break after Friday as well. So then the next meeting will be after the next Friday, after the spring break, which is, I think, will be in March 11th. Okay, and important tables. Which is table 3.1, table 3.2. Those are in page 96 and 97. We already discussed this, and we will keep discussing them. Keep mentioning them during Laplace transformation. So these tables are very important in our analysis. Now, before continuing the properties, let's just give some more examples about the poles and zeros. So I already explained what are poles and zeros. Let's do some examples and see how we can solve it in more complicated way. So we have x of s equals 3s plus 12 over s squared plus 6s plus 15. So we need to find the poles and zeros. So for the first one, for the pole, for the zeros, look at the numerator, then the zeros the denominator. So to find the zeros, 3s plus 12 equals to 0. Therefore, move it to the other side. It will be negative 12 over 3. In other words, will be negative 4. That's the zeros. While the poles, s squared plus 6s plus 15 equals to 0. How to find this? This is as a quadratic equation, like as squared plus bs plus c equals 0. Therefore, s will be negative b using the general formula over 2a plus minus the distinguished, which is b squared minus 4ac. Then now we can substitute a as 1, b as 6, c as 15. So it will be, which is negative 6 over 2 plus minus the square root of 6 squared minus 4 times a1 times c 15. So it will be as negative 6 divided by 2 plus minus square root of 36 minus 60 divided by 2. So which will be as negative 3 plus minus square root of negative 24. So we have a square root of negative number. This means this number will be a complex number. So it can be as negative 3 plus minus square root of negative 1 square root of 24. In other words, it will be negative 3 plus minus j, because when the square root of negative 1 is j, and here the square root divided by 2. Square root of 24 divided by 2, and which is going to be as negative 3 plus minus j, then it will be as negative 24, which will be 2 square root of 6 divided by 2. Then 2 will cancel each other, so the answer will be negative 3 plus minus j square root of 6. So we can know that, look at this, or you can notice this, that the poles are negative 3 plus j6, and its conjugates, negative 3 minus j6. So we know the conjugates, right, from the complex numbers. So you will see that whenever we have a complex number, you need to have unit plus p1 j squared of negative 1. Whenever you have a whole pairs, this will be complex conjugates. Complex and its conjugates. It must come the poles as pairs. The complex with its conjugates. For a causal system or for a real life system, if there is any complex pole, there must be its conjugates. Is a must for real life system. Then if we need to plot this in the xy plane mode, then we have here the location of the 0 at negative 4. So here is negative 4. The 0 is O. We draw it as O. While the poles we draw as x. So for the imaginary part, we have here j square root of 6. Here, negative j square root of 6. Then for the real part at negative 3, here is negative 3. Then the intersection comes here. Then this is location for this. And I can just erase this line just to make sure that we know where we're at. Then this is this is the real part of S, this is the imaginary part. So when we see that there's a complex conjugate, which is there is whenever there is plus j, like for example, like we have here negative 3 plus j square root of 6, then there must be another one, negative 3 minus j square root of 6. Okay? Now, how can we do this in MATLAB? Actually, in MATLAB it can be easier, so I don't need to do the math. So how? We will just define the numerator and denominator. So in MATLAB, you need to put the coefficients of each one. So again, here is x of s. We have it as 3s plus 12 divided by s squared plus 6s plus 15. So let's define the coefficient as a vector. So the coefficient of the numerator equals to 3, 12. So it is this vector has only 2. The dimension of it is 2, or the length is 2. Then the denominator, it's 3 because we have 15, 6, and 1. So just define the coefficients. So it will be as 1, 6, 50. After that, we need to find the zeros. So the zeros are the roots of the numerator. So we will say zeros equals to the roots of numerator. Then if we need to find the poles, they are the roots of the denominator. And this can be for any equation. If it's quadratic, if it is higher order polynomial, like third order, fourth order, fifth order, etc. It can be for any order. For any higher order, sometimes for higher order we cannot do it in our analysis. Like if you have 5 or fifth order polynomial, so you cannot do it in your life. So what should you do? Basically, you can use MATLAB. Then the MATLAB will find the answer, and that's the MATLAB code to solve this thing. So just keep in mind there is a roots. And how you define roots, and that's it. And you can use it not only to find the poles and zeros, you can use this code to find any roots of any polynomial that you have, which makes your life easier. I don't need to use the calculator or other stuff, because the MATLAB can do the whole job. Okay? Another example. Find the poles and zeros of this function. X of s equals 2s squared plus 10s plus 12 divided by s squared minus 1, 5. I think minus 2s. Okay, how to find the poles and zeros? Let's see. If we want to use the MATLAB, the life will be easier. So we can say like the numerator equal to 2 10, 12, denominator equals to 1, negative 12, and there is should be plus 0 because it's a missing here, the constant, so we will put 0. Keep in mind to put that 0 here because we need to put them in order, okay? Because here there is a missing, again as plus 0. Then we will find like the roots. We will say zeros equals the roots of numerator. Then poles equal to the roots of denominator. Then that's how we find it using the MATLAB. How about if we use the analytical tool? So let's look at the numerator. So the numerator, we have 2s squared plus 10s plus 12 equals 0. How to find s? Using the general rule, which is negative b over 2a square root of plus minus square root of b squared minus 4ac, which is going to be as negative b, which is here b as 10. So negative 10 divided by 2a. A here is 2, so 2 times 2, 4. So plus minus b squared, 10 squared, minus 4ac, minus 4 times a2 times c, which is 12. Then how to find this? Basically it will be as negative 10 plus minus square root of 100. Then 4 times 12, 8s. 8 times, I'm sorry, 4 times 2, 8. 8 times 12, how much? 8 times 12. Can you do this on the calculator? So this 4. 2 times 8, 16, so 96. Square of 100 minus 96, so here we will say it is negative 10 plus minus square root of 4 divided by 4. The square root of 4 is 2. So s will be negative 10 plus 2 divided by 4. Or, this is s1, or s2 equal to negative 10 minus 2 divided by 4, then it will be as negative 10 plus 2, this will make it as 8, negative 8, negative 8 divided by 4 will make it negative 2, and here negative 2 minus, negative 10 minus 2 will be negative 12 divided by 4 will be negative 3, so therefore the poles are negative 2 and negative 3. I'm sorry, those are zeros. That's for the numerator. Now let's go to the denominator. Denominator, we have s squared minus 20, or minus 2s equals 0. So let's take s as a factor. So it will be s minus 2 equal to 0. Therefore the answer will be s equals 0 or s equal to 2. Then we will say that the poles are at s equals 0 or 2. Okay? Now we plot this. Here is the x1 node. And we will see that this is the imaginary part. This is the real part. So the poles are at 0 and 2. So here's 0, here's 2. Then we have here is negative 1, negative 2, negative 3. The zeros are at negative 2 and negative 3. Negative 2 and negative 3. Okay? Then that's how we do the plots for the S-plane. Any question? Now, keep in mind, when you do the zeros, you will put O's, draw them as O's. When you do the poles, make them as X, okay? This is a must, otherwise your answer is wrong. If you put the poles as O instead of X, this is wrong, okay? Let's go to more transformation, Laplace transformation. So one of the properties in the Laplace transformation is about the sine and cosine. So cosine of omega t, u of t, we need to do the Laplace transformation. But how to do the cosine? We know in the Laplace transformation how to do the exponential. So we know the exponential, the Laplace transformation of the exponential. E power at equivalent or equal to 1 over s plus a. That's what we know in in the exponential, which is the regular one. But what we have here, we put this negative a, so what we have here is the cosine. How can we find the cosine using the exponential form? Try to convert the cosine as an exponential form. Are you aware of Euler formula? So just recall Euler formula. What's Euler formula says? E power j theta equals to cosine theta plus j sine theta. Or whenever we see e power negative j theta equals to cosine theta minus j sine theta. Okay? We know this from Euler formula. Then there is a result about the sine and cosine. So we will say that cosine theta will be e power j theta plus e power negative j theta divided by 2. And at the same time, if we need to calculate the sine theta equal to e power j theta minus e power negative j theta divided by j2. So you should be aware of this, all of these four equations now. How we can find them. So the sine or cosine can be found using the Euler formula. You will use this a lot in Laplace transformation. So I encourage you to memorize them because we will use them a lot. All of these four equations: e power j theta, e power negative j theta, cosine theta, sine theta. So you will not only use them in this course, you will use them in future courses. You will use them later in communications and control system and other things. So this is something very important and very essential. But again, like this course is also essential and it's important. Then the target is to convert cosine now to the exponential using the Euler formula. Now theta here equal to omega t, so we will just use this formula but make it as omega t. So it will be as Laplace transformation of cosine, which is e power j omega t plus e power negative j omega t divided by 2, then u of t. Okay? How to find this Laplace transformation? I encourage you to try. So we have a multiplication and addition, so let's try multiply u of t both e power j theta, e power negative j theta. Let's try to do it. So basically, we will do it as 1 over 2. This constant will be outside of the transformation. Then we put a large bracket. So e power j omega t u of t. That's the first Laplace transformation plus Laplace transformation of e power negative j omega t u of t. Then we close the brackets, and this is the big brackets. So according to Laplace transformation in table in the properties, in table 3.2, we have e power negative a t u of t. The Laplace transformation is 1 over s plus a. So we can realize that here, the first one, it is a positive, so the Laplace transformation will be 1 over s minus a. Well, since this one is negative 1 over s plus a, but substitute a as j omega. So it will be as equal to 1/2 times 1 over s minus a, which is s minus omega t, comes with j omega. Then plus 1 over s plus j omega. Okay? Divided by 2. Now, we will not stop here. We will try to simplify it more because most likely we don't prefer to see j in the denominator and numerator, and there is also a positive sign. Let's try to make it as just denominator or numerator denominator. That's what we want. We don't want to see the addition, subtraction, and the other things, so it can be easier for us to find the poles and zeros. That's our target, is to make it in a format such that we can find the poles and zeros easy. So how to do this? Basically, we have s plus j omega, s minus j omega, and there is a positive sign. So what we will do is try to multiply by s, by the conjugate for each part. So it will be 1 over s minus j omega. So I'm going to multiply by s plus j omega over s plus j omega. Then we still have the positive sign here, 1 over s plus j omega. So what we will do is something we call multiply by the conjugate, s minus j omega over s minus j omega. Okay? So by doing the multiplication by conjugate, what will happen here in the denominator? For the denominator, it is s minus j omega times s plus j omega. So it will be s squared minus j omega plus j omega plus, or it is actually minus j squared omega squared. So j omega and minus j omega will cancel each other. So it will be s squared minus j squared, which is the square root of negative 1 squared, root of negative 1 square. So j squared is actually negative 1 times omega square. So the answer will be s squared plus omega squared. That's for the denominator. Okay? So as a result, we don't need to do this every time. What we're going to do every time, when you multiply by the conjugates, the denominator will be s squared plus omega squared. That's it. You didn't need, so the j will be removed. Okay? That's our result. So what will happen? It will be 1 over 2 times s plus j omega over s squared plus omega squared, and the other part, which is plus s minus j omega. Okay, what will happen here? J omega and j omega will cancel each other. S plus s equal to 2s. So it will be 1/2 2s over s squared plus omega squared. 2 1/2 will cancel each other. So the final result will be s over s squared plus omega squared. That's it. That's the problem. So as a result, we will say that it's already been written in the table, but we can also say that, which is the Laplace transformation of cosine omega t times u of t equals to s over s squared plus omega squared. Now, if you need to find the poles and zeros, it can be as s over their conjugate, which is s minus j omega, s plus j omega. Therefore, we will say that zeros at s equals 0, poles at s equals the roots of the denominator, which is j omega, negative j omega. So if we need to plot this in the xy plane mode, or like in the imaginary or s-plane, some people call it s-plane, which is real and imaginary part. So here is like the 0. Here is the 0, which is at 0. Then we have here j omega poles at negative j omega. That's how the sine and cosine. That's how the cosine. Okay, so how about the sine? You can do it. You can try at home. So Laplace transformation of sine omega t u of t. It's already been exists in the table, like it will be as, I think,
Omega over s squared plus omega squared.
omega over s squared plus omega squared. Okay, so it should be like this. So your turn, prove this. You can try it at home, you don't have time to do it now, but very similar to this. But the thing which is, when you do the exponential, you will do e power j theta minus e power negative j theta over j2. That's what you will do. Then just follow the procedure to get this. Then if you plot it in the x-plane mode, xy plane mode, there is no roots for, there is no zeros. We have only poles at j omega and j omega. Well, there are no zeros. All we said is zero happens at the end. We have only polygons, so there are no zeros. Zeros in the s-plane. There is only two poles. Okay? Let's go to properties. So it's frequency shift. So this frequency shift happens if the system is causal, if x of t is causal, and that's what's most likely what we will assume in all of our systems. Because there is no real life system uncausal. We cannot create a system depending on the future. The present depending on the future. As a real life system. Then, we have a Laplace transformation of e power at x of t. So, how we prove this if it will make a frequency shift? Basically, try to do the Laplace formula, which is the integral between negative 0 to infinity, e power negative at x of t, e power negative st dt. Then, we can merge e power negative st, e power at. So it can be as the integral from 0 left to infinity, x of t, e power negative s plus a t dt. Then this is equivalent to, since this is the constants, we can assume this as s1. So it will be as the integral from 0 left to infinity, x of t, e power negative s1, that I assume here, t dt. This is the Laplace transformation definition, so it will be x of s1. Now substitute s1 as s plus a. This yields to be x of s plus a. Okay? So basically, what they did a frequency shift. So as a result, we will say whenever we have e power at x of t multiplied by a function, not the exponential value of t, by the function alone, this will be make it x of s plus a. Make a frequency shift. Yes?
So frequency shifts along the x-axis of the Laplace plane. What does the vertical direction mean?
Imaginary axis. So s basically we have, it's a complex number. So we have a real number, which is the x-axis. The y-axis is the imaginary. So this is frequency shifts. This is happens for the function s, and it can be either in any axis. It can be in x or y, or it can be in imaginary, or it can be on real part. So it's not necessarily to be very axis. Okay, let's try to apply an example. Laplace transformation of e power negative 10t cosine omega t u of t. Now, we have exponential times a function. So like it looks like negative equal negative 80 x of t, right? So basically, it will be, since we have this exponential, it will be as x of s plus a. That's our goal. So let's try to find x of t alone, convert to x of s. So x of t equals cosine omega t, right? Then x of s is, for the cosine, s over s squared plus omega squared. Is this correct? Now let's do x of s plus a. Here, I just want to make sure this is times root of t. X of s plus a. X of s plus a will be s plus a over s plus a all squared plus omega squared. Okay, does this make sense? Now substitutes the values. Then we will say that since a here is 10, a here is 10, so it will be s plus 10 over s plus 10 squared plus omega here, it's not given, so plus omega squared. That's it. So using the property. Okay, does this make sense? That's how we plan our answer. So sometimes, like we don't need to do the integral for everything unless you've been told prove this or find the using the integral. While just try, our target, we try to learn how to apply these things by doing just using the tables. So the tables has a toolbox. So use whatever you need from that toolbox. Now let's go to another property about the time differentiation. All of them are in table 3.2, page I think 97, 98. But now we're just going to go through derivation of this time differentiation. So time differentiation, when I have a derivative, Laplace transformation of a derivative d by dt of x of t. So we will get a result. We can use it instead of making this derivation. Well, let's do the derivation to find the proof. So this is the integral from 0 left to the infinity dx of t by dt e power negative st dt. So dt and dt will cancel each other. What will happen? It will be the integral from 0 and then left to infinity e power negative st dx of t. Okay. Now how to do this integral? It will be as x of t e power negative st between 0 left to infinity minus the integral 0 left to infinity x of t d of e power negative st. Okay, then x of t e power negative st, let's try to substitute from 0 left to the infinity. So it will be as x of infinity e power negative s of infinity minus e power negative s 0 left times x of 0 left minus the integral from 0 to infinity x of t e power negative st times negative s dt. Basically we did, what I did is let this go out from dt by applying the derivative and put it here. So x e power negative infinity, as we know, equals to 0. Then 0 minus e power negative s e power 0 will be 1. So times 1 times x of 0 negative minus the integral from 0 to infinity. So here, negative s x of t e power negative st dt. We can put negative s outside of the integral. So the answer will be here, negative x of 0 minus s will be positive plus s, the integral from negative 0 to infinity, x of t e power negative st dt. This is the definition of Laplace transformation of x of s. So the answer will be negative x of 0 plus x of s. Or in other words, we can redo it as, or rearrange the terms, will be s times x of s minus x of 0. So whenever we have the derivative d by dt of x of t, this yields to be s x of s minus x of 0. So the derivative of a function, we will make s and subtract by minus x of 0. So x of 0 here is related to what? To the initial condition. So sometimes the initial condition can be 0, sometimes it's not 0. So if it is 0, then if initial condition equals 0, this yields to be x of s. But not every time the initial condition is 0. You can imagine like the initial condition of the capacitor, it can be sometimes 0, it can be not. So like that, as you learn in circuit analysis, sometimes you can have or you cannot. So depending on what you had before. Okay? Now, how about the doubling the derivative? So another property, the double derivatives, which is Laplace inverse of x double prime of t. So what we are going to do in order to overcome this, let's define y of t equals the derivative of x bar of t. Therefore, x double bar of t equals to y bar of t. So we can say that in order to find Laplace transformation for y, we can say y of s equal Laplace transformation of y of t, which is Laplace transformation of x bar of t, and the Laplace transformation of x bar of t is what? S x of s minus x of 0. Then let's do Laplace transformation of y of t, y bar of t. So Laplace transformation of y bar of t, let me rewrite it. So x, as a Laplace transformation of y prime of t equals to s y of s minus y of 0 left. Now we already know y here. S x of s minus x of 0. So let's substitute them here. This yields to be s between brackets x of s minus x of 0 negative, then minus here y of 0. So it will be as let's see here, y of 0, we know y equal to x bar, so y of 0 left, I can write a different color, y of 0 equals x bar of 0 left. Okay, so bar is the derivative, then it will be minus x bar of 0 lifts. Let's do the simplification. It will be s times s squared x of s minus s x of 0 negative minus x bar of 0. Okay? So we will set we have two initial conditions. One of them for x of s bar, one of them for x of 0, then we have s squared. So when we have higher order, you need to have two initial conditions. Something that you've learned when you did the differential equation course. When you have first order, you need to have one initial condition, second order, two initial conditions, third order, three initial conditions, and so on. So that's how we do it. Okay, does this make sense? Now, how about let me just summarize this. Whenever you have double derivative x double prime of t, or sometimes we can write it as a dot, double dot of t. So the Laplace transformation can be as s squared x of s minus s x of 0 minus x dot of 0. And we used to put negative means from 0 lifts. Now, let's try to do the derivative on this example. So, example, the Laplace transformation of delta prime of t. What we know about delta bar, or delta prime of t? We used to know it in the signals on the previous example. What's the physical meaning for it? Ideal differential. Now let's see this ideal differentiator. How will it be on Laplace domain? So basically, since it's derivative, it will be as s x of s minus x of 0, right? So it will be as equal to s Laplace transformation of delta of t, that's x of s, minus delta of 0 negative. So delta of t, Laplace transformation of delta of t equal to 1. So the answer will be s minus delta of 0 lifts. What's the value of delta 0 lifts? We call delta function at 0. This is delta of t. Then 0 left is located here. So the value is what? 0. So it will be s minus 0, therefore the final answer will be s. So the Laplace transformation for the ideal differentiator is s. So this is something important that you will really use in the future in order to do the differentiator s as a differentiator, as an ideal differentiator. Then you will also realize to do the ideal integrator is 1 over s, because u of t, which is 1 over s. How about ideal double integral? Double integrator, which is r of t. This is u of t times u of t, which is going to be as 1 over s times 1 over s, so it will be 1 over s squared. Okay? So in summary, I can summarize them in a table. Okay, here is like, also for information, this table 3.1 and 3.2, that has all of this information, but yeah, in these lectures I'm going through explaining them. So, as a result, here is x of t, here is x of s. So whenever we have x of t as delta prime of t or delta bar of t, this is ideal differentiator. So it will be s. whenever we have delta of t, we used to say when we do the convolution, it will be as is, nothing with it, so it will be 1. Whenever we have y of t, which is for ideal integrator when we did the convolution, so it will, which is 1 over s, then r of t, this is double integral when convolution, which will be as 1 over s squared. Okay? Again, all of them are mentioned in the two. Okay, let's do also another property. It's the time integration, because we spoke about everything. Let's see just the time integration. It should be 1 over s squared, but let's prove this. Time integration. So whenever we have x of t, it will be as x of s, then the integral from negative 0 to t, x of tau d tau, d tau will be as 1 over s, x of s. Okay, so let me just try to write this example. Whenever we have delta of t, the Laplace transformation is 1. U of t, which is the integral from 0 to t, delta of tau, d tau, this is 1 over s. Then r of t is the integral from negative 0 to t, delta u of tau, d tau, u of tau, d tau. This is equivalent to 1 over s times 1 over s, which is 1 over s squared. That's how we apply this. Then, before ending the lecture, let me just end up with this example. Let me give a few seconds to write. Then, I'll start the example. This example, we have this function x of t given as 0, 1, 1, x of t, here is t. So our target is to find the first thing, which is x of Laplace transformation of x of t. Then the second thing, Laplace transformation of x prime of t. So let's do the first one, which is Laplace transformation of x of t. The best thing to do the Laplace transformation, because we are in frequency domain, we don't need to use the time domain, so I don't want to do the plotting. So the best thing is to convert x of t into a function, into a formula. What's the formula of x of t? As a step. So x of t will be u of t minus u of t minus 1. Does this make sense? Now, let's do the first thing, which is Laplace transformation of x of t, which is going to be as the Laplace transformation of u of t minus the Laplace transformation of u of t minus 1, because we can distribute the Laplace transformation. Laplace transformation of u of t equal to 1, what's 1 over s. Laplace transformation s of t minus 1, there is a time shift. That time shift will be converted into exponential, which is 1 over s equal negative s. If you need to validate this, go to the table and see the properties, how we do with the time shift. When we have the time shift, it will be as exponential. Then it will be 1 over s between brackets 1 minus equal negative s. Now the second thing, we need to find Laplace transformation of x prime of t. So you have two ways. The first way to find the derivative of the actual function and find Laplace transformation, or we can find the Laplace transformation using this approach, which is s x of s minus x of 0 left. So which is going to be as s times 1 over s 1 minus e or negative s minus x of 0 negative. Then it's going to be as 1 minus equal negative s minus x of 0 negative. X of 0 negative go to this function. So x of 0 negative equal to 0 by looking at this x of t. So this is equal to 0. So the answer will be 1 minus equal negative s. That's the number 2. Or for number 2, you can find x power of t, which is the derivative, because we have x of t as u of t minus u of t minus 1. The derivative, this is delta of t minus delta of t minus 1. Then let's do the Laplace of x power of t, which is delta of t 1 and delta of t minus 1, 1, and there's exponential equal negative s, which is going to be as 1 equal negative s, the same answer. So both of them are correct. And equals. So see you on